Hi, my name is Shahnawaz. This is the first lecture of an elementary course on algebraic geometry. So we'll start this course with this code. Algebra is written geometry and geometry is drawn algebra. So this is a code from by Sophie Germain. Now let us see this code in action. Suppose, for example, let us consider the plane, complex plane, and suppose we are given a circle. So this is the complex plane and this is a circle. Say x square plus y square is equal to 1. Now this is the geometric version of this circle. Now we can look at this circle as the quotient ring C, I mean the polynomial ring in two variables over the field K modulo by the ideal generated by x square plus y square minus 1. So this is called the coordinate ring of this circle. Now we will discuss these rings in more detail in the upcoming lectures. So this is the geometric version of this side and this is the algebraic version. Now roughly speaking, algebraic geometry is a study of geometry of the set of common zeros of a set of polynomials. So algebraic geometry is the study of the set of common zeros of a set of polynomials. Suppose we are given a subset of polynomials. So let us first of all let us consider the polynomial ring over the ring R. So let R be a commutative ring with the identity element. So whenever we say a ring, we always mean these two things, the commutative ring and with the unity. So and consider a subset, say S of the polynomial ring with coefficients in R. So this is the polynomial ring in n variables, and this S is where this S is given like this. So S is just the collection of polynomials in variables x1 extra xn x1 etc xn, where so this is in the polynomial ring x1 through xn such that this lambda is in some index set, say lambda. So now what we do, so we look at the set of common zeros of the polynomials in this set. So we associate with S the set of points in Rn, which is the Cartesian product of n copies of R, the set Zs. by ZS, here we mean the set of common zeros of the polynomials in set S. That is why it is set ZS is given as. So it contains all n tuples in Rn such that when the polynomials in set S are evaluated at these points, they just vanish. So this is true for all lambda in lambda. So we have two objects here. So we have the geometric side and we have the algebraic side. In geometric side we consider the ring Rn, which is just Cartesian product of n copies of R, and here we have the polynomial ring in n variables. We consider here a set, say S, of polynomials in R, and corresponding to this set we get a subset Z of S in Rn, which is just the set of common zeros of the polynomials in S. So this association, so the main purpose of the algebraic geometry is to study this interplay between these two objects. How to translate algebraic properties of this set into geometric properties of this set and vice versa. Now there are some problems that we need to address. Suppose we are given polynomials in R, the polynomial ring R with n variables, in the polynomial ring Rx1 through xn. It may be possible that the polynomials does not vanish at any point of the ring Rn. For example, let us consider our polynomial ring R to be the set of real numbers, and let us consider the polynomial ring Rx. So here we have just one variable, and let us take S here, which is just the polynomial x square plus 1. Now one can look at this as this is a subset of R. Now since this polynomial in Rx does not vanish at any point R, so corresponding to this set S over the zero set is empty. So this is the case which is not of much interest, because to study the geometry of empty set is meaningless. So to handle this situation we always so when Z of S is empty, the situation is hopeless. Now to handle the situation, to handle this situation, we just take our fields to be algebraically closed. So we consider polynomial rings over fields which are algebraically closed. One can note here the field R of real numbers is not algebraically closed. Now if we consider the same polynomials but in the ring, say, I mean, if we take the polynomial in the ring cx, I mean the polynomial ring over the field C, then the zero set of S is non-empty. So here we have this. So corresponding to this set S, the zero set of S is non-empty. Now we have a lemma which is like this. So let S be any subset of polynomials in the polynomial ring in n variables, such that the zero set of S is non-empty. Then there does not exist a finite subset of this set S which generate 1. Now what do we mean here? So then there exists no finite subset, say f lambda 1 through f lambda, or let us call these f1 through fm, f1 through fm in S, and polynomials say g1 up to g m in the polynomial ring R, such that this set over here, this generate 1, such that sigma I goes from 1 to m, fi gi is 1. So this is not true. I mean, if this zero set of S is non-empty, then no finite subset of S generates this 1. Now why this is true? So the proof of this lemma is straightforward. So proof, so suppose such a subset of S exists. Suppose such a subset f1 through fm of S exists. Then for the polynomials g1 through gm in the polynomial ring in n variables, we have say fi gi, where I goes from 1 to m, so this is 1. But since this collection of polynomials over here, they belong to S and zero set of S is non-empty, that means these polynomials vanish at each point of Z of S. So since Z of S is non-empty, let us take some point, say in that n tuple in Z of S. So one can note here all the polynomials vanish at this point. So clearly fi of this n tuple, I mean when we evaluate each polynomial in this set, at this point we get 0. So this is true for all I goes from 1 to m. So hence we have 0 is same as f I of a1 through an gi evaluated at a1 through am is m here, where this I goes from 1 to m. So this is 0, but at the same time, by hypothesis, this is 1. So that implies 0 is 1. So this is not possible. So hence, so this is absurd, because in this case 0 is not equal to 1. So 0 can be equal to 1 when the ring is 0 ring, but here we have a polynomial ring which is non-zero ring. So this is absurd, since 0 is not equal to 1. So hence no such subset of S exists. Now the converse of this result is true if the ring R is algebraically closed. So now the converse of this theorem states that if R is an algebraically closed field, and let S be any subset of polynomials in the polynomial ring such that no finite subset of S generates 1, then 0 set of S is non-empty. So the converse is true if R is an algebraically closed field, and this converse is called the Hilbert's Nullstellensatz. Now I mean, this is not the stronger version. This is sometimes called the weaker form of Hilbert's Nullstellensatz. So let us pen this down here. So this is the Hilbert's Nullstellensatz. So this is actually a German term over here, Nullstellensatz, because this term was given by Hilbert, and this means, so null here stands for the zeros, Stellen stands for the position, and Satz means a statement. So this is the Hilbert statement of the position of zeros. So this is the weaker form. So it says that if K is an algebraically closed field, and S is a subset in the polynomial ring in n variables, such that, so let us call, so let K be an algebraically closed field and S be a subset of this polynomial ring over K. So if no if no subset of S generates the element 1 in the field K, then the zero set of S is non-empty. So this theorem This theorem guarantees us that if we are working over the algebraically closed fields, then we can do geometry. So from now on, we will always work over algebraically closed fields. Now, uh, so now our algebra side will look like, so the commutative algebra side will involve the polynomial rings, say in n variables, over the fields k, which are algebraically closed fields, and the geometric side is the space Kn, which is the Cartesian product of n copies of K. So this is sometimes called the affine space. So uh, one can look at this set. So this is actually a finite dimensional vector space over K. In particular, it is the n-dimensional space. Now there is difference between the affine space and the vector space. So what is the difference between affine space and vector space? This difference is quite subtle. I mean, they have slightly different automorphism groups. So we usually denote the affine space. So if we have the field K, which is given to be algebraically closed, so we define the, we denote the affine space Kn by An, where this is the field K. I don't know the reasons why it is noted by A, maybe for some historic reasons. So so as I said, they are the same thing, but this has the vector space structure, this has more than the vector space. In vector space we just have to mention the origin, because vector space is all about the vectors, and a vector makes sense when we fix the origin. But in affine space we just don't care about the origin. So let us write this down. So there is a subtle difference between the affine space and vector spaces. So the automorphism group of the vector space Kn is simply the group of all invertible linear, so this is actually the group of all invertible linear transformations, which we denote by the set GLN K, which GL means here the general linear group of n cross n matrices with entries from the field K. So for n is equal to K, for n is equal to 2, an element in this group will look like this. So it has 4 entries over here. But as far as the affine spaces are concerned, so the automorphism group of AN, so AN as a set, they are same, but they have different structures. So this contain the automorphism group of Kn. So this is generally group of Kn plus it also contains the translations because uh, a linear transformation is supposed to fix the origin, and a translation by some non-zero element does not preserve the origin. So that is why we include translation here. So this is only possible when we don't care about the origin. I mean, when we just consider origin as an arbitrary point. So an element here will look like, so for n is equal to 3, an element here would look like this. So in this portion over here, this contains the automorphism group of Kn. So this corresponds to this thing over here, and this thing over here, this corresponds to these translations, where a vector v is translated to v plus v naught, where v naught is some fixed vector. So the difference is roughly speaking, a vector space has an origin, and in affine space we forgot what the origin is. So we have vector spaces and we have affine spaces. So from vector spaces to an affine space, we can go by just forgetting the origin. And from affine space to vector space, we can come back by, so we can choose any point to be the origin. So choose any point to be the origin. So what do we do now? So for an affine space, we are just worried about the points in the space. However, in Kn, I mean in the vector space, so I forgot to mention over here. So this automorphism group over here, I mean this space over here, this has the dimension n square, where this has the dimension n square, which comes from this thing over here, and the dimension of this group over here, which is n, and which is same as n times n plus 1. Now to study the geometric structure of Kn, so we have two sides here now. We have the polynomial ring in n variables, and corresponding to this set over here, we have the affine space. Now we can look at this set as the functions from the affine space an to an, where this f is a function which evaluates each element over here at the points of an. Now to study the geometry of an, what we do, it is better to introduce, I mean it is better to topologize an. Now to embed a topology on an, to equip an with the topology, there are two ways. One way is to exhibit a collection of sets which are open sets, and the other way is to exhibit a collection of closed sets, because by De Morgan's law we can go from open sets to closed sets by just taking the complement. So now while giving topology to an, we call that topology the Zariski topology. Now what are the closed sets of an with respect to this topology, or the open sets with respect to this topology? So what we do here, so if we have this polynomial ring over here, and we just take a set S of this field. Now K being algebraically closed, so Hilbert's null status guarantees that the zero set of S will be non-empty. Now what we do, we consider these sets, these subsets of an to be the closed under the Zariski topology, and this by mm, by topologizing an, I mean topologizing an by taking the closed sets as the set of common zero loci of a bunch of polynomials in Sn. So to be the sets of common zero loci of a bunch of polynomials, then this collection over here, this satisfies all the axioms of being a topology. I mean the whole set an and the empty set, they are the closed sets, because this an, this is this zero set of the zero polynomial, and this empty set over here, this is the zero set of a constant polynomial. So both are the closed sets under this topology. We'll discuss this topology in detail, but this is just an introduction. So I think we will start in the next lecture by discussing this topology in more detail.